Hello, everyone. Good afternoon, good night. Now we're going to have our last talk in the number theory session. And it's a pleasure to announce Professor Lucas Reis from Federal University of Minas Gerais. And he will talk about character sums estimates over affine spaces applied to existence results in finite fields. Lucas has several papers in this area, and I thank you, Lucas, for accepting our invitation.
Okay, thank you, Mateus. I would like to thank you, you both, Emad and Mateus, for the invitation. And so this talk is about character sums over finite fields, and we'll be mostly interested in the applications of the results. And so here is an outline of the talk. We start with introduction to characters, and then we move to bounds on character sums over affine spaces. And then we talk a little about primitive elements and what we can say about the existence of primitive elements in affine spaces, considering the new bound I will present here in section 2. And after that, I just present two main applications of the main results. So just to start with some terminology, FQ always denotes the finite field of Q elements. Q is a prime power. FQ to the n is always the n degree extension of FQ. Chi usually denotes a multiplicative character of FQ to the n. I will always use the letter V for an FQ vector space. It's always contained in FQ to the n. And similarly, I'll write an affine space as U plus V, right? So I have a shift of a vector space, and we also allow U equals 0. So when I talk about affine spaces, I'm also including vector spaces. And also for a set S, S between two bars denotes the cardinality of the set, and IS denotes the indicator function. So it's 0 if the element is not in S, and 1 otherwise. Okay, just to start with some basics about characters. We just define a multiplicative character of FQ. It's just a homomorphism from FQ star to C star. Right, so FQ star here is just FQ minus 0. It's well known that this is a group with respect to the product. So it's just a basic definition of a character of a group. And also we have another structure, another operation in FQ. We have the addition plus, and FQ with this operation is an abelian group, and we can also define additive character in the same way, a homomorphism from FQ to C star. So just some basic facts about multiplicative characters. We'll be mostly interested in multiplicative characters in this talk. We just recall that the FQ star is a cyclic group of order Q minus 1, and any generator of this cyclic group is called primitive element. And actually, indeed, from primitive elements, we can just describe the set of all multiplicative characters of finite field. So here's the procedure. We take theta, a primitive element of FQ star, and then we define this function from FQ star to C star. So essentially, we have this index K here. K is an integer between 0 and Q minus 2. And so we define this function. We take any a generic element of FQ star. Since theta is a primitive element, this generic non-zero element is a power of theta, so theta to the j. And so I just define chi k at theta to the j as eta to jk. And eta is a primitive Q minus 1 root of unity, right? So it's direct to verify that these are multiplicative characters of FQ, and in fact, this describes all the multiplicative characters of FQ. We have an interesting character here when we take k equals 0. So it maps every non-zero element to 1. So this is the trivial multiplicative character. And we usually extend the multiplicative characters to the 0 element by just mapping 0 to 0. So just to start as a motivation, characters of finite fields, it's an important tool for proving many results from different areas, including number theory, combinatorics, and arithmetic dynamics. Here is a very nice book just showing the applicability of characters and here you can find many problems, techniques, and results. So in this talk, I'll just be motivated by a special kind of problem. There appears in general, in this kind of thing, we try to prove an existence or a distribution of special elements in finite fields. So in a typical procedure to prove some existence or distribution results, we just use indicator function of a set that are of our interest, and we try to obtain a character sum formula for this indicator function. So here are some examples. We have the set of squares in a finite field, normal elements, primitive elements, elements with prescribed trace, etc. And so in general, we actually try to combine multiplicative and additive properties here. For instance, squares and primitive are basically multiplicative properties of elements in a finite fields, and normal and zero trace are additive. And so here is a typical problem. We just consider two sets, A and B. They are just encoding two properties, right? So A is the set of elements with property 1, and B is the set of elements in FQ with property 2. So we just want to verify if there is some element satisfy 1 and 2. So we just want to prove that A cap B is non-empty, right? And so essentially, we try to compute the number of elements in the intersection, right? So by means of indicator function, the number of elements in A cap B will be this sum, and can also be written as T sum or T sum, right? So there are two main kinds of results. We have existence results. So if you want to prove that A cap B is non-empty, we just need to prove that this sum is positive, right? Because this is always an integer, right? Actually, always a non-negative integer. So it's sufficient to prove that it's greater than 0. And also distribution results. So this is kind of thing that appears in maybe a probabilistic point of view. We just saying that A and B are independent sets. So the properties encoded by them are somehow independent. This is kind of results we also see in the literature. And so just going back to of what I said in the previous slide, we have we try to express indicator functions by means of characters. So at the end, we just have the sum of a character running over a special set of elements, A or B or something like this. And so in general, we usually need to find a non-trivial bound for sums like this, right? So I have a set S that is of my interest, and I have a character chi here, and I need to bound this sum, right? But by non-trivial, I mean the following, right? We just observed that characters, the values are taken like roots of unity, right? So our complex numbers of model 1. So this is a trivial bound, right? We just use triangles inequality. We have this bound, but we usually need something like this, right? So most of the results are set S has some structure. So we're just moving the size of S to infinity, and we want to prove that this character sum is little o of the cardinality of S. Okay. Just to mention, if S is a generic set, this is very hard. Actually, we don't have control on this sum, so it can be very close to the cardinality of S, and maybe this bound can be false, right? Just to mention some well-known results from number theory, we have the most basic one that we take a prime field, right? And S is an interval of integers. So we have the well-known Pauli-Vinogradov bound. We have a small improvement, a nice improvement by Burgess. There is this bound, we just save this quantity with respect to the cardinality if S is not too small. Here is a kind of an extension of intervals to non-prime fields. We call the box. What is a box? Well, if we take any extension of FP, say FP to the K, FP to the K is a vector space over FP, and we have a basis here, any basis, B1, Bk. And so by box, we just mean linear combinations of these, the elements on these bases with the coefficients lying some nice intervals, right? So I'm not going to mention the results. There are many, many of them, depending on the conditions we pose on the intervals I. But this talk is about bounds on affine spaces. Just to mention that the results on boxes cannot apply to affine spaces in general because they do not fit in this definition. And and then I'll just move to the main results, to bounds on affine spaces. We have some previous results to special vector spaces. So here's just to mention, we can save a little from the trivial bound for under some special conditions, but I want you to focus on general results. And so here there is a theorem from 2016, but I think this bound is known for at least 15 years ago, but the proof in this paper is very nice. It states the following. We have A here, an affine FQ affine space of dimension T, and chi is a non-trivial multiplicative character of FQ to the n. And so essentially this sum is never larger than Q to the n over 2, right? This is a constant pretty close to 1. And so essentially here we have a bound that is absolute, right? It doesn't depend on the size of the affine space, right? The affine space of dimension T, we have Q to the T elements. And so this theorem is saying that the character sum never exceeds Q to the n over 2, right? So particularly this bound is non-trivial if T is larger than n over 2. And so the main idea here goes back to what I said before about indicator functions. The author just considered this sum can be rewritten as this one, right? So I just summing over the elements of A. So I just plug the indication function of A. And actually the indicator function of A can be expressed by means of additive characters of finite fields. And so at the end, here's a multiplication character. And so at the end, we just have mixed sums of multiplicative and additive characters that are called Gauss sums. And we have some bounds on the model of Gauss sums. And so, as I said before, if T is larger than the bound is non-trivial, but fortunately, it will be trivial if the affine space is of dimension at most n over 2, right? So the aim of this job is just to present a small improvement of this, that we can just overcome this restriction. But although it's a small improvement, we can prove some very nice results. So before I proceed to the result, I just need to define this. if I take an element alpha in FQ to the n, I say this element has degree n over FQ, or eject FQ to the n, if alpha is not contained in any subfield FQ to the n, which is smaller than n, right? So in other words, in the sense of extinction fields, right, this is a primitive element, but not the same primitive I defined it at the beginning of the talk. And so considering elements of degree n, we have a very nice result from that. They just give a non-trivial bound for the character sum, right? So I'm just taking the translates of an element of degree, right? So that is an element of degree n over FQ. Chi is non-trivial, right? We always take non-trivial characters, otherwise this sum is trivial, will be just the size of the set. Here, FQ will be Q. And so chi non-trivial, that's an element of degree n, and so we have this bound, right? So if I sum the character of the FQ translates of eta, this is always at most n-1 times square root of Q. So in particular, this bound is non-trivial if n is little of square root of Q, right? So essentially, this result is interesting if we are moving Q and n to infinity, right? And whenever n is little of square root of Q, this is non-trivial. So just employing is a straightforward application of what we can get first result. I take and find space of dimension T, and n is greater than 1. And so H divisor D can just call n the number of elements in A whose degree equals D. So I'm just grouping the elements of A according to the degree over FQ, right? So I'll just call n AD, the number of elements in each group. And so if chi is non-trivial, multiplicative factor of FQ to the n, I have this bound here, right? So this is a double sum. I'm just considering all the FQ translates of the elements of A, right? So I sum B in FQ. And so I have this bound here. So appears the number n AD times delta chi d. And delta chi d will be Q if the restriction of the character FQ to Q is trivial. Otherwise, we have this other function, right? And so this is just a straightforward application. I just employ cats, this bound from cats whenever it's possible. And so that this is not actually first equation. But the second inequality is very interesting. In particular, if I have at least one element of degree n, right? So I'm just saying that NaN is positive, I can get this bound, right? So this bound here contains the size of A times Q, right? So Q to the T plus 1. So the trivial bound will be Q to the T plus 1. I just get n times Q to the T plus 1/2, right? So I'm just saving something, essentially is a square root of Q over n. Just to mention, I'm not going to get the details of the proof. Here we strongly use the fact that A is an affine space. So essentially we prove that if A is an affine space and it contains an element of degree n, then it contains many elements of degree n. And from this bound of cats, I can say a lot in the characters. So we have a lot of constellations whenever we have many elements of degree n. And so just to move to a more generic, because here I just I'm not taking actually sum over an affine space. I have these translates of elements in affine space. So just to mention a more clean version of this theorem, I just define this. Affine space here U plus V, right? So V is a vector space U as an element in A. I say that this affine space is N if I can find an element Y and V and Z and A such that Z Y inverse is an element of degree n over FQ, right? And so just rephrasing the previous theorem, I have this this statement. I take A and then define space of dimension T, at least one, And if I take chi a non-trivial character, multiplicative character of FQ to the n, then this factor sum in modulus by this function, right? Just to give an idea of the proof, I just picked 2 elements I and Z here in the definition of and so I just consider the affine space elements from A and multiply by Y inverse, right? And basically, if I just multiply the elements of A by a constant, the character sum won't change, right? Recall that this will be just Ki Y inverse, so chi Y inverse goes out with the modulus is just 1, so this we have this inequality. But now this affine space AY is very interesting. Well, I just have that I can write AY as UI plus VI, right? So it's just A is U plus V. So I'm just dividing U and V by m of V. So Y inverse times V is an element that contains the element 1. And since this is a vector space, it also contains the whole base field FQ. So in particular, this is a vector space containing FQ. I can write in this way. Right? So AY is a direct sum FQ plus B, where B is another affine space of dimension -1. And so essentially, I can write now this new affine space AY is a double sum with another affine space. And so I can just apply the result from the first version of the theorem. So just to recall the statement, we observe that this is non-trivial and is a little of square root of Q. And now just to move that, we have this condition here, right? I'm assuming that this affine space is n good, right? I just want to show that this in this range of non-triviality of this bound, this n goodness. This property we ask is not restrictive in the sense that if an affine space is not good, then this vector sum actually reaches the trivial bound, right? So whenever the trivial bound is not reached, we always have this inequality. So this is by this auxiliary result. We have a fixed Q, a prime power, n at most Q. Then either my affine space is n good, or it is contained in a special vector space of this form, right? Y times FQ to the G, which is divided n, d strictly smaller than n, and by an element of FQ to the n. So I'm not going to give the proof, but it's just a combinatory argument to just make a counting argument and show that this is true. So if we consider the range of non-triviality and little O of square root of Q, or n at most square root of Q, we have actually n at most Q, so we can apply the proposition, right? So if under this inequality, if my affine space is not in good, which means that I cannot use the theorem, we have this, right? So AY, I just define as taking the same I here. So Y minus 1 times A. Since A is contained in this vector space, we have AY is containing FQ to the G, right? So essentially, I just take the character sum over A, right? It will be the same over AI, but now AI is an affine space containing FQ to the G, so I can try to apply the theorem again. So I just need to check if AI is G good or the character restricted to FQ to the G is trivial, right? So if AI is not G good, if one of these things happens, I can either employ the bound or I just realize that this sum actually is the trivial sum because the character here is trivial, right? So otherwise, I just iterate this procedure, right? Like I did the first time. So after some iterations, we actually reach, at some point, we have an affine space A star, which is the same character sum when taking the modulus, such that this affine space contained in a subfield FQ to the E, such that either A star is E good or this restriction is trivial, right? And so in conclusion, either we can apply the theorem in initial or we indeed have the this equality, right? So the character sum actually reaches the trivial bound, which is the size of it. Now just moving to a very interesting remark regarding this and goodness. I observe the following. If I take Pn as the smallest prime divisor of n, then I have this property, right? If I take n divisor of n, is strictly smaller than n, then d is n over p, right? So recall that n good prime space is always contained in spaces of the at most a divisor of n which is not n, right? So essentially, if I take space greater than the greatest by n, n of p,
Lucas,
always be n.
excuse me.
So if I have a straightforward result, I can see that my affine space is n good, so I can apply the non-trivial bound of character sums. Yeah.
Yes. Parece estar
Can
falhando.
You hear me?
Yes, we can. But it seems that em alguns momentos está falhando um pouco a fala. Você acha que, não sei se é só para mim, mas talvez tenha alguma sobrecarga na internet?
Eu não sei. Tá melhor agora?
Não, agora está falhando, né? Quando você fala, corta várias palavras, né?
Esse último slide eu não consegui ouvir, estava cortando bastante. Será que travou?
Você está congelada agora a sua imagem, né?
Estão conseguindo me ouvir agora?
Sim.
A sua imagem está congelada, né?
Talvez parar de compartilhar rapidamente.
Minha tela travou aqui.
Tá. Será que você corta a sua imagem e vê se melhora? Que aí fica menos uma coisa na internet,
vou tentar
né?
agora. Vou tentar agora.
Agora eu tô te ouvindo perfeitamente. Tá bem limpa a fala.
Tá. Só deu uma agarrada aqui, eu vou tentar sair logo.
Não, tranquilo. Sem pressa. Lucas, a tela voltou aqui.
Vocês conseguem me ouvir agora?
Sim, tá bem melhor.
Tá dando para ouvir?
Sim.
Não, beleza.
Talvez só deixar sem a câmera de agora para frente. Porque eu acho que a câmera que estava travando, né?
Acho que ficou melhor.
Beleza,
sim,
Lucas. Desculpa ter interrompido.
Sem problemas. Parei foi nesse aqui, né?
Isso.
Foi nesse slide? Tá.
Acho que você consegue voltar só um para... Isso, acho que foi aqui. Isso, foi isso mesmo. Beleza.
Onde? Eu já tinha terminado? Deu para
Sim,
escutar
tava...
tudo até o final?
Sim,
Okay.
sim. Aí começou a travar bastante no próximo slide.
Beleza. Okay. Just going back. This is a straightforward application of these n-good affine spaces, we can just use a dimension argument to verify that an affine space is always n-good, right? So from this proposition, we have that if an affine space is not n-good, then it is contained in a vector space of this form, right? So y times fq to the g, where d is a proper divisor of n. So in particular, d is at most n. So this is a bound for the dimension of A, right? So if the dimension of A is greater than any proper divisor of n, then this affine space is always n good, right? And so the largest proper divisor of n is just n over Pn, where Pn is the smallest prime divisor of n, right? So in particular, if I take an affine space of dimension larger than n over Pn, this affine space is n good. And so just a straightforward corollary, we have that if A is an affine space of dimension larger than n over Pn, then I have this bound on the character sum. Something that I just mentioned earlier, this bound is nice, non-trivial if n is fixed and q's goes to infinity, right? So essentially, I'm improving the bound by this quotient, right? So square root of n. This is what I'm saving from the trivial bound. So if I fix n and q goes to infinity, I'm saving something actually effective in the character sum. So now just moving to the applications to primitive elements, I just recalled that an element here in fq to the n is primitive if generates the cyclic group fq to the n star. And so now just something that I said at the beginning of the talk, right? Here we want to prove the existence of primitive elements with special properties. And so we actually have a character sum formula for the indicator function of the set of primitive elements, right? This result is from Vinogradov. And so we just have this expression, right? So here are the characters. We have here the Möbius function, Euler's function. And so essentially this sum here, I take W, any element of fq to the n, this sum equals 1 if and only if W is primitive. Otherwise, this sum will be 0, right? These are the functions I mentioned, they are pairs. And here, the sum is of all the multiplicative characters of order exactly d. Right, and so just employing this indicator function, this is a very nice result that we can just get straightforward. So I fix n a positive integer and epsilon is something positive. And so there is a constant depending on n and epsilon such that for any q larger than this constant and every n good affine space A in fq to the n, right? So n is fixed, q is large enough, and A is a generic affine space that is n good lying in fq to the n. And so essentially this proposition is saying that if this affine space has dimension g, at least 1, then the number of primitive elements in A is at least q to the n minus epsilon. So this just means that if n is fixed, q is large enough, any affine space in fq to the n that is n good contains a lot of primitive elements. So the proof is quite simple. We just plug the indicator function, right? So PA is the number of primitive elements in A. I just sum the indicator function with W over A, right? So I'm summing over all the W's in A. I want to find the elements in A that are primitive, right? So it's just the sum of the indicator function. And so I just replace the indicator function by this sum, right? And so I just get this sum. I just normalize here, just multiply something to get this triple sum. And so I just separate here the trivial character where I just have the trivial bound. And so in here, I just pick the non-trivial characters. And so essentially, I just employ the bounds we have. And so it just makes some calculations. I'm not going to give all the details. Here's the function W that appears. It's just the number of square-free divisors of q to the n minus 1. This is just because the Möbius function is 0 whenever the divisor is not square-free. So the sum only counts when G is a square-free divisor of q to the n minus 1. That's why it appears this function, but we have some trivial bounds for the function W and also the Euler function. So at the end, we just we can get this lower bound. So from now on, all the results will be asymptotic. So we assume that n is fixed and q is large enough. And so here is a generic theorem that we can obtain from this proposition. That says the following. It basically characterizes the affine spaces containing primitive elements. And so if I fix n at least 2, I have a constant here, Cn, such that if Q is larger than Cn, so the field is large enough, a generic affine space in Fq to the n contains a primitive element if and only if one of these two conditions hold. First one is that A is n good. So A contains the elements y and z with that property I just defined. Otherwise, A contains a primitive element y, and there exists a divisor D smaller than n such that A is contained in this subfield. So this affine space will be very specific, right? This is just a straightforward application of the proposition. I'm not going into the details. And so just a remark, as we have seen that any affine space of dimension larger than n over Pn, where Pn is the smallest prime divisor of n, always contains a primitive element as long as Q is large enough. Okay, so I have two applications. I think I will have only have time to say a little about the first one. And so this is actually the main motivation, and I just studied these bounds on affine spaces. I was just reading some papers on primitive elements with prescribed traces. And so this is essentially this thing, digits of finite fields is just motivated by the case of integers. This is a very famous and serious number theory work, right? We have here probably the two main works on digits of finite of integers, right? So we just take the expansion of an integer in some bases, we have digits. And so we just ask about squares and primes with prescribed digits, things like this. So we have here the works of Mauduit and Hiva. And so motivated by this setting over the integers, I think it was a paper of 2013 or 14, something recent by Dartige and Sarkozy. They defined it what is digits over finite fields, right? And so here's the definition. We take the field Fq to the n. This is we can regard Fq to the n as an Fq vector space of dimension n. And so if we take a basis here, B1 to Bn, if this is a basis, every element of Fq to the n can be written as a sum like this, where each ai is an element of Fq. So these are just the coefficients. But now if I just take the basis, I order the basis B1 to Bn, we say that A1 to An is the digits of y with respect to the basis B, right? So it's just a definition, natural definition from a basis of a vector space.
Lucas? Acho que o Lucas caiu, pessoal. E Márcia, consegue ouvir?
Eu estou aqui. Mas realmente desconectou, né? Ele está aqui na sala, né? Deve estar tentando se reconectar, né? Vamos aguardar um pouquinho.
Vamos sim.
Conseguem me ouvir agora?
Conseguimos, Lucas.
Tá. Acho que agora vai. Até onde vocês estavam conseguindo me escutar?
Bem aí mesmo, quando você estava falando sobre os dígitos.
Beleza. Okay, so we have this thing on prescribing digits, right? So we just consider a special subset of FQ to the n. So we just choose some positions, J1 to JK, K positions. And so at these positions, I prescribed the digits, right? So at the position A, J1, I want the element C, J1, where C, J1 is an element of FQ, right? And so we have many works dealing with special elements with prescribed digits. So I'm just taking sets of these four, right, like S, and I'm asking if I have squares, images of polynomial functions or primitive elements, etc. In this set S, right? So I'm just asking if there is a square in FQ whose some digits are pre-assigned. And so here is a nice reference to this work, and we have many references there referring to prior work since this 2014 paper. And so this is a very natural question, considering the setting of digits over finite fields. Here we fix n, and q is large enough for how many digits can we prescribe? Right, so for what values of k at most n, we can prescribe it, k digits of a primitive element in FQ to the n, right? With respect to an arbitrary basis, right? And so in 2018, Swain-Opel in this paper proved that we can roughly prescribe half of the digits, right? So if we pre-assign half of the digits in any order, any digit prescribed, we can always find a primitive element. And so, but now we can take this problem and move to the context of affine spaces, right? And so observe that if we prescribe k digits in certain k positions from 1 to n, the resulting set is an FQ affine space of dimension n minus k, right? Why is that? Observe that if I take two elements of this set S, right? Their difference, if I take the difference between them, in those positions I just pre-assign will be 0, right? And the others will be anything, can be anything, right? So in particular, this is a vector space, right? Of dimension exactly n minus k, because I have zeros in k positions, and the others I can do whatever I want, right? And so in particular, the set of elements with k digits prescribed is an FQ affine space of dimension n minus k. And so we just recall that this will be n good if n minus k is larger than n over pn, where pn is the smallest prime factor of n. And so this is the same as saying that k, we can guarantee existence up to n minus n over pn minus 1. And so if n is even, this is just saying that k is at most n over 2 minus 1. So we just go back to the Swain-Opel's result. But if n is odd, we can get a very nice improvement, right? So from n over 2 here, if n is odd, pn is at least 3. So I get only k smaller than 2/3 of n. And of course, if the smallest prime factor of n is very large, I can get something pretty close to n, right? So essentially, if n has only large prime factors, I can prescribe a very big proportion, close to 1, of the digits and still have a primitive element. And so just to finish, I just mentioned that this bound here is actually shard. We cannot prescribe exactly this number plus 1, right? And so what I'm saying that I cannot prescribe n minus over pn of the digits of a primitive and still guarantee a primitive element. And so this is the counter example is a construction. I just take the subfield. This is actually very common when we are studying character sums. We always have triviality if we consider subfields, right? Because the character could be trivial in the subfield, but non-trivial in the larger field. And so essentially, this is also appears as the counterexample for this. I just take this subfield. This is the maximal subfield of FQ to the n, FQ to n over Pn. So this subfield here is a vector space of dimension n over Pn over FQ. I just take a basis here, B1 to Bn over Pn. And so I just complete to a basis to the whole space FQ to the n, right? So here we have n over Pn elements, and the C's are n minus n over Pn elements. And so here I'm trying to prove that I cannot prescribe n minus n over Pn digits, right? So what I do here is I just prescribe the digits corresponding to C1 to Cn minus n over Pn to be 0, right? So the affine space I'm considering are just linear combination of the B's, right? But any linear combination of the B's will be, again, an element of this subfield, because the elements, the Bi's are just comprise a basis for this subfield, right? And so any combination of the B's will be, again, in the smaller field. So we cannot have a primitive element in this subfield, right? You cannot generate the whole field. So I'm just gonna to stop here. I can share the slides if anyone is interested in the second application. Here are the references, and that's it. Thank you very much. Obrigado.
Thank you a lot, Lucas, for this nice talk.